Welcome to This Explainer. Okay, so have you ever wondered how a modern AI recently broke a mathematical expectation that had stood for literally nearly 80 years? And here's the really fascinating part. It didn't do it just by calculating faster or by crunching more numbers. Actually, it did it by structurally changing how it thinks.
So how exactly do you break a long-standing mathematical expectation? Think about it. If you're trying to solve a famously stuck problem, history shows us that the answer usually isn't found in the obvious familiar landscape where everyone else has been looking. You really have to look elsewhere.
Section 1. The unit distance problem. Trapped in the Euclidean plane.
Let's set the scene in this flat, dense, geometric landscape where mathematicians have basically been walking down the exact same paths for decades. We're going to dive into this simple-sounding question, first posed by Paul Erdős way back in 1946. It goes like this. Place n points in the Euclidean plane. Among those points, how many pairs can be exactly 1 unit apart? I mean, it sounds deceivingly simple, right? You can explain the whole premise in just one sentence. And for decades, the standard intuition was that grid-like configurations were essentially close to optimal.
What a long-held, near-linear expectation was that this number would be at most n to the power of 1 plus O of 1. But the AI system completely shattered this with a massive breakthrough. It found infinitely many examples yielding at least n to the power of 1 plus delta, which was later refined mathematically to a delta of 0.014. That might sound like a tiny shift to some, but it completely changed the energy of the whole problem.
Section 2. Crossing mathematical domains. Finding the gradient jump.
Now, the deeper significance here wasn't just finding a new, concrete bound. The true achievement, the real game changer, was identifying a neglected route between two completely different mathematical domains. On one hand, we have the expected surface search space of combinatorial geometry, things like point configurations, grids, and incidence bounds. But the AI made a massive gradient jump to a deep, distant route in algebraic number theory. We're talking about connecting those geometry concepts to incredibly deep structures like infinite class field towers and Golod-Shafrevich theory. It revealed that the problem's true search space had been completely misread all this time.
This kind of discovery requires a very specific flow. First, you start with the surface problem. Second, you extract the true underlying constraint beneath the surface wording. Third, you find an alternative mathematical representation. And fourth, you route that search energy toward distant domains to create a cross-domain route. By extracting the hidden constraint, the system didn't just rely on superficial analogies. Instead, it actively and purposefully jumped domains.
Section 3. The energetic paradigm. Architecture for discovery.
So how on earth do we actually govern this cross-domain jump? Well, we need essential infrastructure. The energetic paradigm, or EP for short, is exactly that. It's a reasoning, control, evaluation, and discovery architecture. It absolutely does not treat AI research as some magic answer generator where you just type in a prompt and boom, get a proof out. Instead, it treats it as a governed energy routing system where attention, computation, and evidence are systematically and carefully directed.
To actually make that jump, EP pushes the system to rigorously reframe the original constraint. The geometric condition of distance equals 1 gets completely transformed into a representation problem of fixed norm differences. Essentially, the problem is now placed into a new alternative mathematical environment, where the search gradient is much steeper and, frankly, far more productive.
Section 4. Discipline over chaos. Uncontrolled search versus EP governance.
Because let's face it, AI models can generate all sorts of wild ideas, but surprise alone is incredibly cheap. An uncontrolled AI system frantically generates many surprising connections. It has high search activity, sure, but it's incredibly noisy. It produces plausible-sounding mathematical language, but it often hides non-constructive gaps or completely broken assumptions. Ultimately, it gives no reliable conclusion, and it wastes immense computational energy on superficial analogies.
So the crucial takeaway here is how an EP-governed system operates entirely differently. It enforces a constraint-preserving representation shift, it uses targeted domain routing, allows for the early rejection of elegant but invalid paths, maintains highly traceable evidence, and, most importantly, results in an expert-verifiable construction. It strictly filters out the noise by governing the reasoning path and distinguishing operational connections from mere analogies.
It achieves all of this through strict deductive verification checkpoints, things like the Euclidean plane, exact unit distance, infinitely many constructions, and asymptotic improvement. Any reasoning path that violates these precise invariants is visibly terminated immediately, no exceptions. This deductive control prevents precious energy leakage into attractive but completely invalid routes.
But what about the dead ends? I mean, under EP, failure memory means dead ends are not simply discarded. For 80 years, mathematicians tried familiar directions and got stuck. EP maps those failures as structured search memory. It actively asks which representation was exhausted or which bound remains stuck, deliberately avoiding repeating the community's old mistakes, just at higher computation speeds.
Section 5. Evaluating true significance, the human audit, and field integration.
Moving into these final stages of the discovery flow, we see how EP converts raw mathematical output into actual field-changing results by heavily filtering it. It evaluates correctness, novelty, explanatory value, and field significance entirely separately. For instance, an output might be formally plausible but invalid, yielding absolutely zero scientific value, so it's rejected early. It might be correct but trivial, which simply gets filtered out. Promising but incomplete outputs? Those require reconstruction. But when an output is correct and field-changing, it has high scientific value and is immediately sent to human audit. You see, EP successfully separates mere formal correctness from true assumption-breaking significance.
As the original researchers perfectly noted, the model proposes or finds a route. Expert judgment verifies the route. The field absorbs the route only when it changes the map of future work. Human mathematicians are absolutely essential at this highest governance level. They're the ones who inspect the construction, explain its context, and actually integrate AI-generated results into the scientific field. Because discovery is an ecology, right? It's not a solo act.
Section 6. The future of discovery, building reliable knowledge.
So, what does this all mean for the future of AI research systems, way beyond just the realm of mathematics? Well, this architectural pattern, extracting a constraint and routing it to a distant domain, it applies everywhere. In biology, we can map a surface disease phenotype to the deeper energy of metabolism or protein folding. In material science, a target property connects directly to lattice structures and defect behaviors. In engineering, surface performance routes to thermal constraints and manufacturability. This is literally a universal pattern for breakthroughs.
To wrap things up, AI found a new mathematical route, yes, but EP turns route finding into a disciplined discovery system. Future AI absolutely must do more than just generate surprising ideas or plausible proofs. It must produce controlled, evidence-traceable, interpretable, and field-changing knowledge. So I'll leave you with this final provocative thought. As AI continues to rapidly expand the search fields of human knowledge, how will we build the architectures that govern the energy of its discoveries, ensuring they don't just give us answers, but actually rewrite our maps of the world?